Okay, so welcome to Nerd Society. Hi, hello. So UPSC 2019 का ये सवाल है क्वांटम मैकेनिक्स. दिस वाज आस्क्ड फॉर 50 मार्क्स. तीन पार्ट हैं इसके 20 प्लस 15 प्लस 15. So we are going to solve one by one all these three parts. So first question is, how do you define density of states so that the density of states with wave vector less than k vector in a three-dimensional cubic box of volume V can be given by d omega is equal to V over 2 pi square k square dk over d omega in the frequency spectrum between omega and omega plus d omega. Here assume that the number of modes per unit range of k is L by 2 pi, L being the length of each side of cubic box. Okay, हिंदी में भी पढ़ देता हूँ मैं. आप ऊर्जा स्तर घनत्व को किस प्रकार परिभाषित करते हैं? दिखाइए कि k वेक्टर का कम तरंग सदिश वाला ऊर्जा स्तर घनत्व आयतन V के तीन आयामी घनीय बॉक्स में d omega is equal to 2 V upon 2 pi square k square dk by d omega. So this is basically this thing. So we are going to start. Okay, so the question has been asked, what is density of state? Okay, density of states. Cool. So in solid state physics, density of states is defined as the number of states available ऐसे कूल तो ऐसे ही लिखा जाता है इसमें. एक मिनट. Okay. Okay. So okay. So we are going to start with the first question, which is define density of states. What do you think about density of states? Okay, density of states. ये आपको define करना है कि क्या है, and then you have to derive density of states. Okay. So in solid state physics, the density of states is the number of states. Okay, the number of states to be states available for the system to occupy at certain energy level. Okay, at certain energy level. So what does this mean? इसका मतलब ऐसा है कि let's say there are three energy states E1, E2 and E3. Okay, so at this energy state E1, how many allowed solutions are there which can be occupied by the system? So allowed solution at this boundary problem. Okay, allowed solutions. State is nothing but a allowed solution of a problem, boundary value problem. So in the locality of E1, how many states are there that can be occupied by the system? Okay, in the same manner, let's say there are less states available here that can be occupied by the system, then we will say that density of states for the energy level E2 is less than E1. Okay, or E2 is less dense than E1. Okay, the same manner, let's say there are very less states that can be occupied at energy level E3, then we can say the density of states is very less in case of E3. So density of states is greater for E1, then E2, then E3. Okay, so this is the definition of density of states. There may be certain energy state where so many states can be occupied, or so many states can be available for the system to occupy, and there may be some energy states where there is no allowed solution, or there is no state that can be occupied by the system. So these two possibilities are there. So what is the use of this density of states? Okay, so we have to write that thing. This definition just won't fetch us marks. Okay, so we have to write something which is different. Okay, so let's say this is energy level E1 and this is energy level E2. Okay, so if we know the density of states at energy level E1, okay, so we can write density of states as a function of energy. Okay, so that we can know that at what energy what is density of state. Okay, so let's say at E1 density of state is high, and E2 density of states is less. Okay, so if we know the density of states of the system, then we can definitely know that how much is this band gap between these energy state is. So from this we can, this is the use of density of states, we can know the spacing between energy bands in semiconductors. Okay, this is the application of density of states. Okay, so we can know the spacing between energy bands in semiconductor, and the bulk properties like specific heat and magnetic susceptibility can be understood by density of states. Okay, density of states can, just tell you about the magnetic susceptibility of the system and the specific heat of the system. Okay, so this is the application of density of states. There are so many applications of density of states in quantum mechanics. There is a very wide room for this concept, or this area, density of state, but we don't have to write so much. Okay, this will be sufficient for this, because we have to derive the density of state. Okay, so in the question, the next thing is we are going to derive the density of state, formula of density of state. Okay, in frequency spectrum, but there is one problem. This density of state can be derived for 1D, one dimension, for 2 dimension, for 3 dimensions. Okay, but the question which has been asked, उसमें आपको 3D मॉडल यूज करके आप डेंसिटी ऑफ स्टेट जो है derive कर सकते हैं. Okay, so I am using a 3D box. Okay, 3D box which is a cube of length L. Okay, each side length is L, so this is a cube. Okay, 3D box. So I suppose that all of you just know the solution for the Schrodinger equation for this 3D box system, which you have done in your course in quantum mechanics. So for this we can write the vibration can be written as EI k dot R. Okay, the displacement can be written as this. Okay, or EI, what happened? Okay, or it can be written as I kxx plus kyy plus kz z. Okay, we can apply the periodic boundary condition over here. The wave function will vanish at ends of this cube, so we can use this, and we can find kx to be 2 pi by L nx, ky equal 2 pi by L ny, kz is 2 pi by L nz. Okay, these are nx, ny, and nz. So, and this is given in the question. Okay, so I've written this thing directly because this thing has been given in the question. The question says there are L over 2 pi modes, number of modes. Okay, so there are L over 2 pi modes per unit range of k. So if I put k, there are L by 2 pi modes. Okay, so this thing has been given in the question. K is given in the question as 2 pi by L into n, which says number of modes in unit range of k is equal to L by 2 pi, which can be written mathematically like this. This line has been written in the question. Okay, and the question says assume this thing, which means we don't have to derive this thing. I have just told you this thing, we don't have to derive, you can just use this thing directly from the question. Okay, and we know that for 3D box, the energy solution for energy is E is equal to nx square plus ny square plus nz square h square over 8 ml square. So for the given system, L is constant, m is constant. This has been solved for the electrons. The mass here is of electron. Okay, h. So this can be written as nx square plus ny square plus nz square. This thing has nothing to do with this derivation, but there is one concept that has to be understood clearly. That's why I'm just writing this thing. So this can be written, this can be shifted here, this can be shifted here. So this will become some constant time energy. So I'm writing this is alpha E root over, I'm writing this is square. This can be written as like this. So that this nx, ny, and nz, x square plus y square plus z square is r square, which is the equation of sphere. So we can know that nx, ny, nz form a spherical surface, are on a spherical surface. Okay, and we know that kx is 2 pi by L nx, ky is 2 pi by L ny, and kz is 2 pi by L nz. So from here we can put the value of nx, ny, and nz. If we put this value here, nx, ny, nz, we will get that the same equation will convert in kx square plus ky square plus kz square is equal to some constant beta square. Okay, I'm not interested in the value of beta. I'm just using this thing that kx, ky, kz also form a spherical surface, so that kx, ky, kz lie on this sphere, and this thing kx, ky, and kz, this is called k space. Okay, so like xyz, we have a k space, the space of vectors kx, ky, wave vectors kx, ky, and kz, so which is a sphere kx, ky, and kz. So this thing, okay, you don't have to write all these things in this question, but I just wanted to use the concept of k space so that you can be, you can just get familiar with what is k space. That's why I have done this thing. So this is k space diagram. So now the question says that for unit range of k, there are L over 2 pi modes. Okay, for this is given in the question, uh, and okay, so question says for unit range of k, there are L over 2 pi modes available, or we can say that in every range of L over 2 pi there is a k point. Okay, so like this we can write it, or we can say that every k is separated by 2 pi by L. Okay, the next k value is separated by 2 pi by L, 2 pi by L, the next value will be at 2 pi by L, the next k value will be at 2 pi, this plus 2 pi L, this plus 2 pi by L. Okay, so between two k points there is a distance of 2 pi by L. So let's assume let's say this is 2 pi by L in x direction, this is 2 pi by L in y direction, this is 2 pi by L in z direction. Okay, so if we form a cube over here joining these points, okay, we can take this point in a cube. So in this volume 2 pi by L, 2 pi by L, 2 pi by L, this means the volume is 2 pi by L whole cube. In this volume contains 1k point. Okay, so the density of states can be written as okay, so this says 2 pi by L whole cube volume contains 1k state, or we can say the density of state is equal to 1k state per 2 pi over L cube volume, which can be written as L cube over 8 pi cube, which L cube is our volume, your volume of the cube, so V over 8 pi cube. This is the density of state. Okay, so this is the density of state for this 3D problem. Now we know that we are interested in k space. Okay, so I'm drawing the k space again. So this is kx, this is ky, this is kz, kx, this is ky, this is kz. So let's assume a sphere here. So I'm interested in finding the number of states available between k and k plus dk. Okay, so this radius is k, this is dk. Okay, so I'm interested in finding the number of states available in this region. Okay, the red shaded area. Okay, in this region, how many states are here in this region? Okay, so number of states, how many states are here? So how should I calculate it? If I know the density, then I have to find the volume. This volume will be, if r dr, then we know this volume will be 4 pi r square dr. So here this volume will be 4 pi k square dk. So how many number of states? Okay, number of states between k and k plus dk. How many states are there? So we know the density, this is V over 8 pi cube, and we know the volume. Okay, so per unit volume this number of states are available. So in volume 4 pi k square dk, these number of states are available. Okay, this can be written as vk square over 2 pi square dk. Okay, cool. Now we know that I am taking the linear dispersion relation, which is k is omega by v. Okay, so omega is k into v. Okay, so omega is equal to k into v. For waves we know this thing, k wave vector is omega by v. So from here I can write, this is the linear. Okay, okay, so from here I know that, so this is say k, this is k, and this is k plus dk. So we know that for this k we can find an omega from here. So this k there will be one omega. For k plus dk there will be omega plus d omega. Okay, so let's say there are there are some states between k and k plus dk, then we can definitely show this, that the number of states between k and k plus dk will be equal to omega and omega plus d omega. So number of states between omega, so the number of states between frequency range of d omega will be equal to number of states between the wave vector range of dk. So d omega is equal to dk. These are the number of states between k and k plus dk which we have find here Vk square over 2 pi square dk, Vk square over 2 pi square dk. Okay, so from here we can show that d omega is equal to Vk square over 2 pi square dk by d omega. Okay, from here we can show this has been asked in the question. From here we can say that d omega is directly proportional to k square. We have used the dispersion relation omega is equal to kv. So from here we can write that d omega is proportional to k square, which means proportional to omega square. So we can say that for linear dispersion relation we have find out a quadratic spectral relation. Okay, quadratic. Okay, this model is also known as Debye model, and we can explain a specific heat from this model. Okay, thank you so much. This was it for today. Thank you so much.